In probability theory and statistics, the geometric distribution is either of two discrete probability distributions. The probability distribution of the number X of Bernoulli trials needed to get one success, supported on the set 1, 2, 3. The probability distribution of the number Y equals X minus 1 of failures before the first success, supported on the set 0, 1, 2, 3. Which of these one calls the geometric distribution is a matter of convention and convenience. These two different geometric distributions should not be confused with each other. Often, the name-shifted geometric distribution is adopted for the former one. However, to avoid ambiguity, it is considered wise to indicate which is intended, by mentioning the support explicitly. It's the probability that the first occurrence of success requires k number of independent trials, each with success probability p. If the probability of success on each trial is p, then the probability that the kth trial is the first success is for k equals 1, 2, 3. The above form of geometric distribution is used for modeling the number of trials up to and including the first success. By contrast, the following form of the geometric distribution is used for modeling the number of failures until the first success, for k equals 0, 1, 2, 3. In either case, the sequence of probabilities is a geometric sequence. For example, suppose an ordinary die is thrown repeatedly until the first time A1 appears. The probability distribution of the number of times it is thrown is supported on the infinite set 1, 2, 3, and is a geometric distribution with p equals 1/6. Introduction to the geometric distribution. Consider a sequence of trials, where each trial has only two possible outcomes. The probability of success is assumed to be the same for each trial. In such a sequence of trials, the geometric distribution is useful to model the number of failures before the first success. The distribution gives the probability that there are 0 failures before the first success, 1 failure before the first success, 2 failures before the first success, and so on. Examples: a newlywed couple plans to have children, and will continue until the first girl. What is the probability that there are 0 boys before the first girl, 1 boy before the first girl, 2 boys before the first girl, and so on? A doctor is seeking an antidepressant for a newly diagnosed patient. Suppose that, of the available antidepressant drugs, the probability that any particular drug will be effective for a particular patient is p equals 0.6. What is the probability that the first drug found to be effective for this patient is the first drug tried, the second drug tried, and so on? What is the expected number of drugs that will be tried to find one that is effective? A patient is waiting for a suitable matching kidney donor for a transplant. If the probability that a randomly selected donor is a suitable match is p equals 0.1. What is the expected number of donors who will be tested before a matching donor is found? Assumptions. When is the geometric distribution an appropriate model? The geometric distribution is an appropriate model if the following assumptions are true. The phenomenon being modeled is a sequence of independent trials. There are only two possible outcomes for each trial, often designated success or failure. The probability of success, p, is the same for every trial. If these conditions are true, then the geometric random variable is the count of the number of failures before the first success. The possible number of failures before the first success is 0, 1, 2, 3, and so on. The geometric random variable y is the number of failures before the first success. In the graphs above, this formulation is shown on the right. An alternative formulation is that the geometric random variable x is the total number of trials up to and including the first success, and the number of failures is x1. In the graphs above, this formulation is shown on the left. Probability of outcomes. Consider the antidepressant example above. The probability that any given drug is effective is p equals 0.6. The probability that a drug will not be effective is Q equals 1, P equals 1, 0.6 equals 0.4. Here are probabilities of some possible outcomes. The first drug works. There are 0 failures before the first success. Y equals 0 failures. The probability P is simply the probability that the first drug works. The first drug fails, but the second drug works. There is 1 failure before the first success. Y equals 1 failure. The probability for this sequence of events is P*P, which is given by the first drug fails, the second drug fails, but the third drug works. There are 2 failures before the first success. Y equals 2 failures. The probability for this sequence of events is P*P*P. The general formula to calculate the probability of K failures before the first success, where the probability of success is P and the probability of failure is Q equals 1 P, is for K equals 0, 1, 2, 3. For the newlyweds awaiting their first girl, the probability of no boys before the first girl is the probability of 1 boy before the first girl is the probability of 2 boys before the first girl is, and so on. Expected number of failures before the first success for the geometric distribution. The expected number of failures before the first success is E equals P. For the antidepressant example, with P equals 0.6, the mean number of failures before the first success is E equals P equals 0.6 equals 0.67. For the kidney donor example, with P equals 0.1, the mean number of failures before the first success is E equals 0.1 equals 9. For the alternative formulation, where X is the number of trials up to and including the first success, the expected value is E equals 1, P. Moments and cumulants. The expected value of a geometrically distributed random variable X is 1, P, and the variance is P2. Similarly, the expected value of the geometrically distributed random variable Y equals X minus 1 is Q, P equals P, and its variance is P2. Let mu equals P be the expected value of Y. Then the cumulants of the probability distribution of Y satisfy the recursion outline of proof. That the expected value is P can be shown in the following way. Let Y be as above. Then parameter estimation. For both variants of the geometric distribution, the parameter P can be estimated by equating the expected value with the sample mean. This is the method of moments, which in this case happens to yield maximum likelihood estimates of P. Specifically, for the first variant, let K equals K1 not be a sample where K1 for I equals 1. Then P can be estimated as in Bayesian inference. The beta distribution is the conjugate prior distribution for the parameter P. If this parameter is given a beta prior, then the posterior distribution is the posterior mean E. P approaches the maximum likelihood estimate as alpha and beta approach 0. In the alternative case, let K1 not be a sample where K0 for I equals 1. Then P can be estimated as the posterior distribution of P given a beta prior as again the posterior mean E. P approaches the maximum likelihood estimate as alpha and beta approach 0. Other properties. The probability generating functions of X and Y are, respectively, like its continuous analog. The geometric distribution is memoryless. That means that if you intend to repeat an experiment until the first success, then, given that the first success has not yet occurred, the conditional probability distribution of the number of additional trials does not depend on how many failures have been observed. The die one throws or the coin one tosses does not have a memory of these failures. The geometric distribution is the only memoryless discrete distribution among all discrete probability distributions supported on 1, 2, 3. With given expected value mu, the geometric distribution X with parameter P equals 1, mu is the one with the largest entropy. The geometric distribution of the number y of failures before the first success is infinitely divisible, i.e., for any positive integer n, there exist independent identically distributed random variables y1, yn whose sum has the same distribution that y has. These will not be geometrically distributed unless n equals 1, they follow a negative binomial distribution. The decimal digits of the geometrically distributed random variable y are a sequence of independent random variables. For example, the hundreds digit d has this probability distribution, where q equals 1 minus p, and similarly for the other digits, and, more generally, similarly for numeral systems with other bases than 10, when the base is 2. This shows that a geometrically distributed random variable can be written as a sum of independent random variables whose probability distributions are indecomposable. Golomb coding is the optimal prefix code for the geometric discrete distribution. The following recurrence relation holds. Related distributions. The geometric distribution y is a special case of the negative binomial distribution, with r equals 1. More generally, if y1, y are independent geometrically distributed variables with parameter p, then the sum follows a negative binomial distribution with parameters r and p. The geometric distribution is a special case of discrete compound Poisson distribution. If y1, y are independent geometrically distributed variables, then their minimum is also geometrically distributed, with parameter suppose 0 less than r less than 1, and for k equals 1, 2, 3. The random variable xk has a Poisson distribution with expected value rk, k, then has a geometric distribution taking values in the set 0, 1, 2, with expected value r. The exponential distribution is the continuous analog of the geometric distribution. If x is an exponentially distributed random variable with parameter lambda, then, whereas the floor function is a geometrically distributed random variable with parameter p equals 1 minus e minus lambda, and taking values in the set 0, 1, 2. This can be used to generate geometrically distributed pseudorandom numbers by first generating exponentially distributed pseudorandom numbers from a uniform pseudorandom number generator. Then is geometrically distributed with parameter, if is uniformly distributed in 0, 1, if, and then we get an asymptotic exponential distribution with parameter of sins. Computer software for the geometric distribution. Geometric distribution using R. The R function DGEOM calculates the probability that there are k failures before the first success, where the argument prob is the probability of success on each trial. For example, DGEOM equals 0.6, DGEOM equals 0.24. R uses the convention that k is the number of failures, so that the number of trials up to and including the first success is k plus 1. The following R code creates a graph of the geometric distribution from y equals 0 to 10, with p equals 0.6. Y equals 0, 10, P, Y equals DGEOM plot. Main equals geometric distribution for P equals 0.6, ILAB equals P. XLABE equals Y equals number of failures before first success. Geometric distribution using Excel. The geometric distribution for the number of failures before the first success is a special case of the negative binomial distribution. For the number of failures before s successes, the Excel function negbinomdist calculates the probability of k equals number underscore f failures before s equals number underscore s successes, where p equals probability underscore s is the probability of success on each trial. For the geometric distribution, let number underscore s equals 1 success. For example, equals negbinomdiste equals 0.6 equals negbinomdiste equals 0.24. Like R, Excel uses the convention that K is the number of failures, so that the number of trials up to and including the first success is K plus 1.